Hi, and welcome to another lab. This lab is going to be about plane wave expansion methods. So the question is, can you calculate the one-dimensional photonic crystal bands for alternating layers of 3 and 1? So we have two different refractive indexes. One is with 3, the other one is 1. And then the total lattice is only 1 micrometer thick, and the higher index material, that is the one with the refractive index 3, occupies 80% of the lattice or has 0.8 micrometer thickness. So the rest, 0.2 micrometer, is for the material with refractive index 1. Okay, so let me connect to MATLAB computer. All right, so here is the plane wave expansion code. We start by entering the refractive indexes, of course, and also the lattice constant speed of light, how much of it is occupied by the higher index material, and then this part gives us basically the total refractive index distribution. And then we take the 1 over epsilon, if you remember, for our plane wave expansion method. Then we take the Fourier transform here. So MATLAB takes the Fourier transform with the code FFT, and then you have to do FFT shift. You can basically watch and see what happens if you do not. If you do the FFT shift, it will put the DC portion, the zero frequency portion, right in the middle of the spectrum. So we are going to take into consideration 50 harmonic fields, 50 plane waves components, and then we are starting to write down the mattress in the same way that we went over in the lecture notes. And then I'm going to try to get the bands, the corresponding band results. Another important thing is the IX command. IX command of MATLAB immediately gives you the corresponding eigenvalues. You don't have to work with F0 or anything else like that. All right, so let's run the code. It's finalized. So let's check a couple of things. First thing I would like to see is the index profile. So let's see how it looks like. Yeah, so index profile looks like this. So it's 0, it's 1 here for the whole 1 micrometer lattice, and then right in the middle it is 3, and there's also 1 here. Okay, it looks good. One other thing you have to do is basically, while taking this FFT, MATLAB allows you to determine the dimension of the FFT. You have to really keep it high. In other words, you have to get a high precision. Of course, if you already have a nice high precision meshing for your spatial domain, that will automatically give you, without really entering any other variables for the FFT of MATLAB code, that gives you high, nice precision already. So the next thing we can do is we can check the bands. Sorry, it was the value. This time it's K wave vector. Yeah, so this gives us this, but let's do the following. Let's plot them in a normalized way for the wave vector, like we did in the last lecture. Yeah, so from 0 to 1. So this is the frequency axis. That is the terahertz frequency range. And this is my K component. So you see that we see the emergence of the band stop bands again here nicely. So if you want to do this similar thing, and or like want to check if you've done it right, what you can do is, let's close this guy. And if you remember, we've done things very similar last lecture, but with the TMM codes. We didn't do plane wave expansion, but we did transmission transfer matrix. So for that, we can run the code, but I already prepared the result for you. So as you can see, once I enter the corresponding values here, let's see what the values were. So my values are, as you can see, it's again 3:1, and 4:1 is the volumetric ratio this time. So that gives me very nice coincidence with my TMM results. The TMM results, which are the markers here, the circles, are coinciding well with the solid lines. And I can do one more thing. I can also check it with my, if you remember, my cascaded layer result. That's the straightforward transmission transfer matrix method. So if we do that as well, bearing in mind that, like, if you put the y-axis to be terahertz, because in the dispersion results that's the y-axis, and this is the transmission axis. So you see, again, we have the band gaps here where we have zero transmission. They should coincide very well. So let's look at it on the lecture slides. Yeah, so if we zoom in, we'll see that, let's close this. We'll see a very nice match between the frequencies that were predicted by the plane wave expansion, also the eigenvalue equation of the TMM, also together with the straightforward TMM result. So they match quite well at the borders. Of course, I just like visually, to the best of my capabilities, I put these roughly, so you can really see that, I mean, where they end, where they start. They have to perfectly match all of them. One more thing that I would like to highlight. So in the last lecture, we were always plotting the dispersion bands with normalized frequencies, reference frequency that was omega 0. So please read this here. You can see how we converted that for a real lattice, one-dimensional lattice like this one. And so we could get now the actual frequencies instead of the normalized frequencies. One other thing is the way that MATLAB takes the Fourier transform. So MATLAB takes it in a way that these components here, the Fourier transform components of the input function fx, are given like this, but they are actually, the Fourier components are defined like this. So when you take the Fourier transform, in other words, in MATLAB, that will give you a higher number than what you are supposed to get, because if you see that this is what we are, that's our definition. Our 1 over epsilon is defined to be like this with the kappas here. Our kappa here is MATLAB's Fourier transform over n. N is the total dimension of the Fourier transform. So that's why you have to divide the Fourier transform results that you will get from MATLAB by the total size of the Fourier transform function. I mean, the function that's going into the Fourier transform, that's the fx there. Okay, so these are the things that I wanted to highlight for this lab. So hopefully see you in the next one. Bye.